Ladies and gentlemen, I'm going to talk about the foundations of deformation theory. First, I shall show that the common theory in the textbooks is simply wrong by all standards known to us. Then I shall give an outline of the theory which I have given. All processes conceivable in classical physics can be sorted into this simple frame. A process that follows the energy conservation law in the upper box is called conservative because during such a process, the total energy remains constant, it is conserved. In contrast, a process during which the total energy of the system is changed is called non-conservative, and the energy conservation law is the first law of thermodynamics. The non-conservative processes may be further subdivided into the reversible and the irreversible classes. This frame is so fundamental that you usually do not find it in textbooks because books are usually written either about conservative physics or about non-conservative physics. I give a few examples for each class. The upper box is generally that of Newtonian mechanics. The lower one is the field of thermodynamics. Now, if we ask where elasticity and stress belongs in this frame, the answer is clear. Elastic deformation is by nature a reversible process. Therefore, it is non-conservative. It must start with the equation of state, and this you cannot find in textbooks. I should point out that the difference between top and bottom is very fundamental. There is no theoretical bridge from top to bottom. The two classes and their energy conservation laws are mutually exclusive. This table gives you all the conceptual tools of Newtonian mechanics and of thermodynamics. They are so completely different that it is fair to say they have nothing to do with one another. This list is worth studying in detail, but right now we do not have the time. I suggest you take a screenshot. I shall highlight only one single item. Work done in a Newtonian process will change both the kinetic and the potential energy, but not their sum. The state of the system is constant. The work is therefore done within the kinetic system. Instead, thermodynamic work is done upon a system. There is no bridge. These two work terms are entirely different in nature. They cannot be added or otherwise related to one another. No matter they have the same unit. They must not be mixed up or otherwise be confused. These two conceptual groups are separate worlds. Violating this systematics is the worst mistake you can possibly make in classical physics. And I shall show that this mistake has been made. The gist of this introduction is elastic deformation is by nature a change of state in the sense of the first law of thermodynamics. But you cannot conclude this from textbooks. This theory is bullshit. We have to see this in the perspective of the history of physics. The concepts used in deformation theory are among the oldest in physics altogether. Euler wrote in 776 and Cauchy in 1827. But this is not modern physics. See what these workers did not know yet. They did not know about physical work yet. They did not know the first law. They did not know about bonds in solids and so on. All this stuff we learn today in high school. But it is decades younger than the deformation theory. How can we think today about physics without the concept of work? What is a solid if you do not know about bonds? This entire discipline is full of concepts that were conceived in the context of Newtonian mechanics for the simple reason that no alternative was around yet. Continuum mechanics simply denies the existence of thermodynamic concepts even 170 years after their discovery. One example is work. Here the red circle is deformed into the green ellipse. Shortening work is done in the vertical and stretching work is done in the horizontal. The two displacements and their work expressions must have opposite sign. And for a volume neutral deformation, they must sum to zero. This zero is inescapable. I have looked at dozens of textbooks and calculated the equations there to the end. The answer is always zero. The current dogma is summarized by these observations here. You find them in any textbook. But what do they mean in the context of modern knowledge? The trace of the tensor is the only part in all this that is physically relevant, and it is zero. The zero sum of the diagonal terms is the equivalent of the Laplace condition in potential theory. It is the mathematically sharpest form to state that no work is done upon the system. The continuum mechanics theory is a perpetual motion theory. It is invalid by definition. And this is not even all there is, or better, there is not. In my introductory class in 1980, I asked the lecturer, how is work done by shear forces? He did not answer. Today I know that this question has never been considered. The question cannot even be asked. How could such a silly theory survive for so long? Newton's third law and the thermodynamic equilibrium condition are two independent principles. But continuum mechanics is simply blind to the concepts of thermodynamics. And this blindness is self-inflicted because the concepts are obviously self-evident if they are only mentioned. This is the only mathematics I shall present to you, and not even in detail. If you only took introductory calculus in your student years, you know about the Gauss divergence theorem. It is one of the most important mathematical laws, and it is always correct. My proof that the Cauchy stress tensor does not exist consists of the proof that Cauchy's continuum approach violates this law. There is no escape. I have published this proof 3 times. This did not go unnoticed, but nobody ever argued against it. The stress tensor does not exist. It is not permissible in mathematics nor in physics to reduce a volume of mass to a point, because in doing so, the geometric relation to space is lost. The loss of spatial dimension in continuum mechanics has the effect that elasticity cannot be logically connected to the concept of work. The effect of work is a displacement in real space. Any potential problem has a real distance term as a property that is required to define work. This zero potential distance does not exist in continuum mechanics. To give a few examples of the zero potential distance, it may be the length of Hooke's spring, or it may be the length of a bond in a solid, or it may be the radius of the thermodynamic system. Without this distance term, physical work cannot be defined. The continuum mechanics theory fails in many ways, but for geologists, especially important is this. The theory fails completely and universally with regard to simple shear. It does not explain any of the observations that are made in simple shear in any realm of material behavior, starting with the concept of simple shear itself. Forget it. One last point to discredit the continuum mechanics theory is this. In my intro class at the University of California, Davis in 1980, I asked the lecturer, where are bonds? There are bonds in solids. Where are the bonds in the theory? He did not answer. In the meantime, I have checked dozens of textbooks. In none of them, bonds were mentioned in the context of stress theory. Why is this so? The stress theory is 70 years older than the theory that than the discovery that bonds in solids exist. What is your definition of obsolete? This theory is bullshit. Why has not one single discussion partner reacted in any way when I pointed out that bonds have been forgotten in the theory of stress and deformation from 1980 to this day? Or are you not at all interested in science? Are you just interested in getting your PhD, your paper out, or your book in print? This question has cost me 40 years of my life. Here are my publications. You may take a screenshot. The one in the red frame is my theory. The others contain my critique of continuum mechanics, which I just explained to you. First step. Conventional thermodynamics is isotropic. It was developed for the understanding of a gas. It can handle increases of pressure or temperature, but direction-dependent properties are never considered. This is done through vector field methods, the theory of potentials. Here are two vector fields. The left one is isotropic. The one on the right is anisotropic. It has two discrete eigendirections with opposite sign. It is not possible to do work on a system in only one single direction. Work is always done in all directions. This may not be obvious at first sight. The one-dimensional equivalent to PDV is the product of force times change of radius, FDR. If this term is integrated over all directions, PDV and FDR give the same result for isotropic boundary conditions. However, the force need not necessarily be a normal force as long as the magnitudes are right. So we can discuss anisotropic boundary conditions with vector fields. Second point, Boyle's law works only for a gas. We need a state function for solids. It looked reasonable to introduce the exponent k. Such an exponent has been used before, but it's rational. At the bottom is new. This k relates the molar volume of a solid to that of a gas. This equation can be checked against reality. Percy Bridgman received the Nobel Prize for reaching 100 kilobar in his experiments. His compressibilities for the alkali elements look like this. Every material has its own curve. But if his data are recalculated using the equation which I've just showed you, it turns out that relative to their internal pressure, all these materials have exactly the same compressibility. This shows that my equation works, which is great, because now I can postulate a hypothetical solid that follows Boyle's law, which is mathematically very simple. And for real materials, the exponent is easy enough to find. We don't need it here. Now, something that cannot be put in numbers, but must be observed in modeling. In a solid, system and surrounding are solidly bonded to one another. This has the most profound importance. It means that in the elastic field, non-equilibrium is by definition impossible. It means that we can find constraints for the shape of the thermodynamic system. In Newtonian mechanics, we need the chief boundary conditions, which are body shape and force configuration. We can then determine if equilibrium exists. Inside a bonded solid, we can turn the question upside down. We have equilibrium and the force configuration. The shape of the thermodynamic system can then be calculated. It is spherical only in the simplest case, but the greatest successes of the new approach were found in situations where the shape is not spherical, especially in simple shear. Last point, we need a field theory. If you have taken linear algebra, that should not be a problem. We need two force fields. The external one represents the external boundary conditions. The internal field represents the material properties. They are entirely independent and must be joined through the bonding condition that equilibrium exists by definition. And this is a list of all the things I could suddenly explain. This is far too much for the short time I'm given here. So a number of things will not be mentioned in this talk. Let's indulge in what interests the geologist the most. Here you see equilibrium of system and surrounding as in standard thermodynamics. And this is what I came up with for the properties of simple shear. It does not look at all like what you would expect. It has a contracting and an extending eigendirection, which are not mutually perpendicular. Eigendirections are directions that do not rotate and that cannot be crossed by a material line. The opposite concept is that of a maximum shear direction, here dotted in red. Not only does it shear, but it is also the direction with the greatest angular velocity. It must rotate antithetically while it shears synthetically. This is important. It means that a stable glide direction does not exist. We must rethink shearing completely. Now, do we find the characteristic? How do we find the? No, sorry. Do we find the characteristic directions of this field here in nature? Plenty. This is a mylonite from in the Alps. In fact, it is the shear zone of California in mathematics in 1980. And I think I solved it. The C-planes are parallel to my maximum shear direction. The S-plane is parallel to my extending eigendirection. It turns out that the eigendirections completely govern the fabric and the kinematics of the rock. This may be surprising to those of you who think in terms of stress and strain, both of which are useless and obsolete. It is not surprising for those who have learned to think like an engineer. Eigendirections are of most fundamental importance and of great use in all kinds of engineering problems. Another example from an eclogite in Western Norway. My hammer is in the circle. Again, the S and C planes are exactly as predicted by my vector field, plus the joints, which are exactly parallel to the contracting eigendirection. In this mylonite, the SC fabric is too small, but look at the cracks. My vector field is absolutely reliable. This works at regional scale as well. Here a map of the San Andreas fault. Once you understand that the measured stress directions are eigendirections, things fall into place. More recent studies from the San Andreas drilling project are shown here. The mean maximum stress direction plus standard deviation are shown by the red line and the orange wedges. These are precisely on my contracting eigendirection. In case you wonder, this is still unpublished. I received an out of scope from General Geophysical Research Letters, Geology, twice from Tectonophysics, Solid Earth, and I did not bother to try the Journal of Structural Geology. Does any one of you know of a journal where this is not out of scope? Here a map of the North Anatolian Fault. See the block tectonics at the bottom. My vector field fits like a glove. The reader's shear faults define long, narrow fault blocks with maximum extension roughly northeast, northwest, southeast. The blocks rotate against the sense of long dimensions into the extending eigendirection, as shown in the inset at the top. Here an analysis of sigma delta clasts in a mylonite from the Himalaya. The blue delta clasts are all in the small sector with antithetic rotation sense, as they should. The red sigma clasts line up with the extending eigendirection. And where precisely is the sigma delta divider line? The red line is that of the original authors, exactly 69 degrees. The divider line in green are from another study from Idaho. The line that divides delta clasts from sigma clasts is precisely along my contracting eigendirection. As stated above, the eigendirections determine the rock fabric. So much for that. I used my theory to calculate the work done in pure shear and simple shear for elastic and plastic deformation. Pure shear work is taken as 100%, and the simple shear work is shown in relation. The new approach predicts that in the elastic field, simple shear costs 8% more energy than pure shear. The predictions fit perfectly with the experimental observations. The difference is well known experimentally, but this is the first time anyone offers an explanation for it. For plastic deformation, there are only very few comparative studies, but they agree that plastic simple shear costs substantially less work than pure shear. Both the sign of the difference of pure versus simple shear and the magnitude of the difference are correctly predicted by the new approach. No other theory comes even close. Considering the principle of least work, pure shear is strongly preferred in elastic deformation. On the contrary, the energetic difference in the plastic field between pure and simple shear is so massive that pure shear should be physically impossible. It should all go in simple shear. And isn't this precisely what we see? My theory explains why shear zones exist in the first place and why they are so extremely narrow. The old theory, in its quaint concepts, does not tell us anything about deformation. The difference between reversible and irreversible material behavior has been completely missed. Elastic deformation is homogeneous since, due to the principle of least work, directional gradients will be minimized. By the same token, plastic deformation tends to be as heterogeneous as possible because simple shear forms conjugate shear zones, thereby maximizing dead zones. Plastic deformation work is bond breaking work, and any bond not energy saved. We shall have to rethink deformation completely. Materials subjected to elastic simple shear dilate. This is known since 1909. The reason is not understood, but you get only so far with an inadequate theory. I mentioned earlier that the work done by shear forces cannot be defined in the Euler-Cauchy theory. My theory does better. The red line is the surface of a thermodynamic system centered at Q, and P is the point of action of a shear force F in orange. The radius vector R is in green. I assume that a shear force displaces its point of action in its own direction from P to P prime. But then all new vectors R prime are longer than R. This is independent of the quadrant we are looking at. It follows that all shear forces have a dilating effect, and the effects of two shear forces with opposite sign does not cancel, but it adds. Dilatancy is simply the effect of shear forces. Now, the surface of the unloaded system is in yellow. The total loading force field has to be partitioned for mathematical reasons into 4 parts. Step 1 is the average loading, which is isotropic. The result is a volume reduction, the red outline. Step 2 is the normal forces only part of the deviatoric field. It causes a further contraction in Z and an expansion in X. The surface is now the inner dark green line. The work done in step 2 by the contraction in Z and the expansion in X cancels. It is indeed 0. Step 3 is the expansion of the system by itself, due to the principle of least work, because it is offered the freedom by the boundary conditions to expand in X. This expansion is caused by the shear forces exerted by the system at the surrounding, and it is positive work. Step 4 is the effect caused by the shear forces of the surrounding upon the system. It has the same effect as step 3. The system expands in the direction of freedom, in this case, X. The final surface of the loaded system is the outer green line. However, for pure shear boundary conditions, the outer green ellipse has the same volume as the original yellow circle. The elastic pure shear deformation is volume neutral. However, the light green area is the expansion caused by the shear forces. I call this the shear dilation. The same decomposition is shown now in PV space. U0 is the unloaded state. Step 1 is the isotropic average loading. The state moves from U0 to U1. Step 2 is energy neutral. It does not leave a trace in the system. The two shear dilations by system upon the surrounding and by surrounding upon the system have the same effect. The system expands, and it expands for pure shear precisely to the original volume V0. Note, however, that the reference state is not U0, but U1. The reference equilibrium volume is therefore V1. At V0, the system is now expanded. For simple shear, the equipotential surface is not a sphere, but an ellipse, which has a larger surface. The expansion by the two shear components therefore creates an expansion beyond V0. That means, relative to the unloaded state, we now observe a measurable volume dilation. This dilation does not start at V0, but at V1, which is the volume of the loaded reference state. That is, if you do not know about this diagram and you only go by the experimental observations, you do not know about the expansion from V1 to V0 in pure shear. You see it only if you perform an elastic simple shear. The shear dilation for pure shear is masked. It follows that any anisotropically loaded system is constitutionally expanded beyond its equilibrium volume, which is V1. The shear dilation is a new, hitherto unknown thermodynamic state function that can be observed only in anisotropic loading. It is the situation that from one starting, all this may change the interpretations of earthquakes profoundly. The drill core data, the blue lines, show that the entire region, 150 kilometers across from the California coast to the Great Valley, is subjected to elastic simple shear. It is therefore volumetrically expanded, which amounts to several kilometers, which is elastic. Since crustal plates cannot just move to the side, this expansion increases the pressure upon the fault, blocking it. At far greater elastic potential can build up than without shear dilation. The energy released during a quake should be proportional to the magnitude of the storing volume of the elastic potential. Furthermore, since the Earth's surface is a solid free space interface, the shear dilation may cause minor elastic uplift. This uplift may be relieved energetically by rupture. The elastic uplift due to simple shear along the fault may indeed cause a permanent tectonic irreversible uplift across the fault and be very real. It is therefore plausible that the uplift of the coast range is an effect of the shear dilation along the San Andreas fault. Also, I should point out that the real San Andreas fault, the fault that moves easily, is not in the crust, but far down in the mantle material at elevated temperature, where plastic simple shear costs far less than energy than pure shear. The crust just follows. Old cold subduction slabs differ from others. They may produce massive earthquakes at great depth. The mechanisms thought feasible so far have no physical basis. Earthquakes cannot be understood by means of a 200-year-old theory that is outdated by 170 years. I mean both Euler's stress theory and Coulomb's friction laws. The deep quakes became enigmatic due to the fact that at great depth, the rock is unable to develop open cracks. Therefore, it was thought to be unable to fracture. In addition, a slab at 1000 centigrade should yield by plastic flow. This sounds reasonable, except that the slab is known to be one of the most water-deficient parts of the Earth's interior. After all, it consists of the oceanic lithosphere that became completely dehydrated by volcanism along spreading centers. Metastable olivine is therefore to be expected. But this has been pointed out before, and it is not my main point. My main point is anisotropic elastic loading causes shear dilation. The lower mantle below the 690 kilometer discontinuity consists of rhystite and perovskite. It is known to be far more viscous than the mantle above it. That is, a cold slab sinking to great depth will eventually hit a mechanical obstacle, the lower mantle. Therefore, it builds up a loading configuration similar to that of a long bar subjected to a compression along its long axis. The shear dilation will develop a maximum above the obstacle in the slab until it yields by precisely the same mechanism as any material that yields near the surface. It is not the opening space that causes the crack, but the imploding shear dilation. Sometimes it does help to pay attention to theory. This is one of three possible causes of deep quakes that come to my mind. Still, they all involve the shear dilation, without which failure cannot be understood, from a wooden toothpick in your hands to the D double prime layer at the core mantle boundary. So, what is a bifurcation? It is the situation that from one starting point, two solutions are possible, which are both equally likely. In the present case, the green path is the elastic loading, which drops suddenly at the elastic limit. And for the subsequent step, there are two possible red paths to follow. Remember the analytic decomposition of elastic loading a few slides back. Here we see the same, but now the view is from above upon the XY plane. In the left panel, the yellow circle is the unloaded state. The first step, the isotropic average loading, causes a volume contraction, the red circle. The expansion due to the steps 2 to 4 is shown in green. Along Y, there is therefore an isotropic contraction and an anisotropic dilation that must cancel for plane deformation. However, because of the anisotropic stretch in Y, which is called by the shear dilation, Y is no longer a neutral direction. In the center panel, only the anisotropic expansion is shown. It is an ellipse with an axial ratio 1 to 3. Now, if a crack or floor is oriented such that it releases the maximum stored energy, the stretches in x and y must combine. But there are two solutions. The stretch in plus x may join forces with the plus y component or the minus y component. This is shown in the right panel. The cracks are expected along one of the two blue lines, but we cannot know which one. There is no floor geometry that can release the entire elastic potential. Rather, upon yield, along one crack, the internally stored elastic potential is suddenly released as a jolt of external kinetic energy in the form of a rotational momentum about z in the xy plane, the sign of which is unpredictable. This bifurcation is a property of the irreversible transition. It occurs every time when this boundary is crossed. Its existence has long been suspected, especially by turbulence researchers. Once again, look at the blue cross in the right panel. Its angular relation shows up everywhere in nature. This is a glacier in Antarctica that floats up when it reaches the sea. The crack is exactly parallel to my prediction. Typically, one arm of the bifurcation dominates the field, the other one shows up at the margin. The same in slaty cleavage. The stretching lineation is visible. Here a hand specimen from this outcrop where the stretching lineation can be better seen. At this scale, only one branch of the bifurcation is visible. A view upon the fault plane of a brittle fault in Turkey. The vertical cracks are indeed composed of two crack directions that follow either branch of the blue cross on the left. The steps formed by these vertical composed cracks form a highly inclined angle to the fault plane. The intersection lines are consistently parallel to the contracting eigendirection of the vector field on the lower right. Please note that the two diagrams are perpendicular to one another. They both share the x direction. The consistent asymmetry makes it easy to determine the shear sense. The far side to the left, the missing near side to the right. Here is a granite mylonite from Saxony. On the left side, the joint directions are a little off. This happens in rocks. On the right side, the same hand specimen seen from the side. Look at the intersection of the joint planes. It is parallel to my contracting eigendirection, and so on. Once you get to look for these directions, you find them everywhere. In the case of the joints, their nature as a result of a released rotational momentum is not obvious. It is balanced by the overall coherence of the rock. However, the release of the rotational momentum during plastic deformation at metamorphic conditions does have an effect. It destabilizes the structural elements parallel to y because, as I pointed out before, y is no longer a neutral direction even in plane deformation. In fluid flow of water, which I shall not discuss today, the bifurcation is the cause of turbulence. In rocks where the bonds are far stronger, the bifurcation is dynamically affected only at microscale. However, I do think that the generation of conjugate cracks, the sheath folds in rocks, and of turbulence in water is due to one and the same mechanism, which is the bifurcation at the irreversible transition and the release of the free rotational momentum. The bifurcation occurs always. Well, the list of items that I would love to demonstrate in detail, but not today. The main points of this talk: the conventional theory of elasticity is obsolete. The new theory is thermodynamics in vector field form and based on the first law. A new thermodynamic state function has been found, the shear dilation. At the reversible-irreversible transition, a bifurcation has been discovered. The new approach is highly successful in its predictions. Finally, there are two incidents that I would like to relate. Back in my students' years in the United States, I once read a geophysical gravity study of the Aleutian Trench in Alaska, done with a surplus submarine right after World War II. The author described with great care what he observed and which questions came to his mind, and it was clear he had not the faintest idea what he was sitting on, which was the subduction zone with trench, heavy slab, and volcanic arc. His ignorance in 1948 was completely innocent, but it was painful to read it in the 1980s. The other one is a visit to the Insubric line and its mylonites in the Val d'Ossola 40 years after my diploma thesis. I caught the mylonite virus back then. It made me go to the United States, take math and physics, and eventually to conceive my theory. Now, in 2018, I stood among those very same rocks, saw the bewildering variety of structures once again, and still, wherever I looked, I could see the physical systematics I had discovered. It is only fair to say, nothing had a stronger educational effect on me than my fieldwork, my exposure to these rocks early in life. Now they spoke to me. I had learned their language. I mean to say, if you are skeptical now, that's your right. But once you have acquired the new understanding and go back to your favorite field area, you will see it with different eyes. And now you will ask yourself how you could possibly miss the order in the structures that jumps into your eye now. For the most part, we only see what we know. But this coin has a flip side. Learning is irreversible. We can no longer be ignorant of what a trench means. Once you understand the shear dilation, you will see a bifurcation in every outcrop. Thanks for listening, and thanks to Rainer Kleinschrodt, who made this talk possible.